Welcome to Module 3, where we start working with files and data. We're kicking things off with a lesson on modules and imports. Over the next few scenes, you'll learn how to organize your code into reusable files and how to pull in built-in, custom, and third-party modules with confidence. What is a module? It's a simple, powerful idea. A module is just a file that contains Python code. Instead of writing everything in one giant file, you organize your code into smaller, manageable files. These can include functions, variables, classes, or executable statements. Why do we use modules? They are essential for organizing large programs, reusing code across different projects, and avoiding repetition. They make your code easier to maintain and allow you to separate different functional areas. In real-world applications, you'll often see dozens or even hundreds of modules working together. To use a module in another file, we use the import statement. Just type import, followed by the module name. Once imported, you can call any function inside it by using the module name as a prefix, like math_tools.add. This keeps your code clean and your namespaces organized. Sometimes you don't need the entire module, just a single function. You can use the quote statement to import exactly what you need. By doing this, you can call the function directly without typing the module name as a prefix, making your code shorter and more direct. If you need several functions from the same module, you can pull them all in on a single line. Simply separate each function name with a comma after the import statement. It's an efficient way to keep your imports tidy, while still having direct access to the tools you need. Python also allows you to import everything from a module using the asterisk wildcard. While this is a quick shortcut, it's generally not recommended for large projects, because it can lead to hidden name conflicts where functions or variables might accidentally overwrite each other. If a module name is long or tedious to type, you can use an alias. By using the as keyword, you can give your module a short nickname. This keeps your code readable and saves you from repetitive typing throughout your script. You can also apply aliases to individual functions. This is especially helpful if you're importing two different functions that share the same name, or if you simply want to make the function name clearer within your code. Remember, the original name still works. The alias just acts as an additional label. Python includes a rich standard library with dozens of ready-to-use modules. You'll frequently rely on modules like math for calculations, random for generating numbers, datetime for time handling, as well as OS and SYS for operating system and environment operations. Let's take a look at the math module. It provides precise mathematical helpers, like square roots, or constants like pi. Just import it, and you have access to a suite of reliable tools for any mathematical calculation your program might need. The random module is essential for games, sampling, and simulations. Functions like randint allow you to generate random whole numbers within a specific range. It's a great example of how built-in modules can add dynamic behavior to your programs with very little effort. When you import a module, how does Python find it? It searches through a specific sequence of locations: the current folder, the standard library, third-party packages, and finally, the paths listed in SYS path. If you ever need to inspect where Python is looking, you can print sys.path yourself. Creating your own module is straightforward. Just save your functions into a new file, and then import that file into your main script. Once imported, you can access those functions exactly as you would with any other module, effectively organizing and reusing your own custom code. Finally, every module includes a special variable called __name__. Its value changes based on how the file is used. It's set to __main___ if you run the file directly, but becomes the module's name if it's imported elsewhere. This is a common pattern for controlling how code executes. So why does that __name___ business actually matter? This pattern lets you write code that runs only when the file is executed directly, and never when it's imported by another file. It is great for tucking quick tests or a demo run inside a module, without triggering them on every import. Beyond the standard library, there's a whole universe of packages built by other developers. You install them using pip. For instance, in your terminal, you can run pip install requests to get started. These packages, like requests, NumPy, and pandas, power a huge amount of modern data and web projects. Let's clear up the difference between modules and packages. A module is just a single .py file. A package, on the other hand, is a folder containing multiple modules. Notice the project structure shown here. The folder contains an __init__.py file, which is exactly what tells Python to treat it as a package. Before we wrap up, remember these best practices. Use clear, descriptive module names and group-related functions together. Avoid import asterisk in large projects to prevent conflicts. Use aliases for long names, and keep each module focused on one clear purpose. These habits will keep your code clean and scalable. Time for some practice. Exercise 1. Build a simple calculator module. Exercise 2. Use the math module to perform specific calculations. Exercise 3. Experiment with the random module to generate numbers. Working through these will solidify your understanding of how to manage modules effectively. To recap, we covered what modules are, how to import them, how to use built-in libraries, and how to create your own structure. We also looked at the __name___ pattern and how to distinguish modules from packages. You've now built a strong foundation for managing your code. Next up, error handling. Welcome to our lesson on error handling. This is a crucial skill for any developer. We'll explore how to catch and manage errors gracefully, so your programs don't just crash when they encounter a problem. Learning to recover from unexpected input or system issues will make your applications much more resilient. What is error handling? Essentially, it is how we prepare for the unexpected. Things like bad user input or missing files are inevitable. Without error handling, your program hits an exception and stops completely. With it, you can catch these issues and keep your program running smoothly. In Python, we generally categorize errors into 3 types. Syntax errors prevent the program from running at all. Runtime errors, or exceptions, occur while the code is running. Logical errors allow the code to execute, but the results produced are incorrect. We focus primarily on catching those runtime exceptions. You'll encounter many common exceptions in Python. Some of the most frequent ones include zero division error, which happens when you divide by 0, and value error for invalid values. You'll also see type error, index error for list issues, key error for dictionaries, and file not found error when a file is missing. The core tool for managing these is the try and except block. You place the code that might fail inside the try block. If an error occurs, Python jumps to the except block, allowing you to define exactly how your program should respond instead of crashing. It is best practice to catch specific exceptions rather than using a generic handler. By defining separate except blocks for errors like value error or zero division error, you can provide tailored feedback for each situation. This makes your programs much easier to debug and more user-friendly. The else block is a useful addition. It runs only if no exceptions occur within the try block. This allows you to clearly separate the happy path, where everything goes as expected, from the error handling logic, making your code easier to read and maintain. Finally, we have the finally block. This code is guaranteed to run, regardless of whether an error occurred. It's the perfect place to clean up resources, like closing files or logging actions, ensuring that your program stays tidy and functional even when it encounters difficulties. Beyond catching errors, you can also trigger them manually using the raise keyword. This is incredibly useful for enforcing your own business rules, such as ensuring a number stays within a valid range. If a rule is broken, you can raise an exception to halt the flow immediately. Let's talk about the messages your users actually see. Clear messages guide the user instead of letting them stare at a cryptic traceback. In this example, we catch a value error and print a helpful message, which improves the user experience and reduces the need for support. Here is a real-world example. A calculator that combines try, except, else, and finally. This single block handles input errors, division by 0, shows the successful result, and cleans up at the end. It's a robust way to manage different outcomes all at once. When handling errors, follow these best practices. Catch specific exceptions, avoid empty except blocks, use meaningful messages, utilize finally for cleanup, and keep your try blocks focused. Avoid the anti-pattern of a giant, empty block, which makes debugging incredibly difficult. Time for some practice. Try your hand at writing a safe division function, and then create a program that attempts to read a file, handling any potential errors like a missing file. Using the file not found error exception is a great way to start. In this lesson, we covered the fundamentals of Python exceptions, how to use try, except, else, and finally blocks, and how to raise your own custom errors. You are now better equipped to build reliable, resilient programs. Up next, we dive into reading and writing files. Welcome to Lesson 3, Reading and Writing Files. This is where your programs finally gain a memory. You'll learn to save logs, settings, and reports, making your data survive long after the program itself ends. Why are files important? Because variables are temporary. To create real-world applications, you need persistent storage. In this lesson, we'll cover opening, reading, writing, and appending to files, all while using the with statement and handling common file-related errors. What exactly is a file? At its simplest, it's a data container on your computer. While there are many types, such as CSVs, JSONs, or images, we will primarily focus on plain text files. These are the foundation for learning how Python interacts with file systems. To work with a file in Python, use the open function. It requires 2 main arguments, the file's name or path, and the mode, which dictates whether you are reading, writing, or appending. Getting these parameters right is the first step in every file operation. Let's review the common file modes. R is for reading, W is for writing, but be careful, it overwrites existing data, and A is for appending. which adds content to the end. These are the three modes you'll use most often when managing data. There are three primary ways to read a file. Read gets everything as one string, read lines gives you a list of every line, and read line pulls just one line at a time. Remember to always close your file once you're finished to release system resources. The most memory-efficient way to read a file is by using a loop. By iterating directly over the file object, Python processes one line at a time. This prevents your memory from being overwhelmed, even when working with very large files. To write to a file, use mode W. If the file doesn't exist, Python will create it for you. Just remember that W overwrites everything currently in the file. Always double-check your mode to ensure you don't accidentally erase valuable data. When writing multiple lines, don't forget the new line character, \n. Without it, all your strings will run together on a single line. Adding that character ensures your output is formatted exactly as you intend. Finally, when you need to grow a file without destroying existing data, use the append mode A. This is ideal for logs and running records. Simply write your new content, and Python will safely place it at the end of the file. So far, we've been calling close by hand every time. And honestly, it's easy to forget. That's where the with statement comes in, and it's the best practice I really want you to remember. When you open a file using with, Python automatically closes it the moment the block ends. The advantages are right here: cleaner code, automatic closing, and it's safer for larger programs. From now on, this is the recommended approach for all your file work. And the good news is that with works for writing just as smoothly as it does for reading. Here we open notes.txt in write mode using with, and write a single line inside the block. There's no manual close call anywhere, and that's the whole point. As the note explains, the file is flushed and closed the instant the block finishes, so your data is safely saved without you having to remember anything extra. Let's talk about what happens when things go wrong. If you try to open a file that isn't there, Python raises a file not found error, and your program crashes. The fix is to wrap the risky part in a try and except block. Here we try to open missing.txt, and if it's not found, we catch that specific error and print a friendly file not found message instead. The lesson on the left: never assume a file exists, always handle the missing case. Now let's clear up how Python finds your file in the first place. There are two ways to point at one. A relative path is written relative to where your program is running, so just data.txt looks in the same folder, and file/data.txt dips into a subfolder. An absolute path, like the full C: path on the bottom, spells out the exact location from the very root of the drive. Both work. You just pick what fits. Let's put a few of these ideas together in a real little example. We ask the user for their name with input, then open users.txt in append mode using with, and write that name followed by a new line. Because we're appending, each name the user enters gets tacked onto the growing list, so the file builds up John, Sarah, Mike, and beyond. At the end, we print a friendly confirmation that the user was saved successfully. Here's another handy example, counting how many lines a file contains. We open the file with, start a counter at 0, then loop through the file one line at a time, adding 1 to the count for every line we pass. When the loop finishes, we print the total. Since our file has 3 lines, the output reads total lines, 3. It's a small program, but it shows how looping and a simple counter combine into something genuinely useful. Before we wrap up, let's look at 2 mistakes that trip up almost everyone. On the left, forgetting to close a file, shown in bad.py where the file is opened but never closed, versus the better version that uses with and handles closing for us. On the right, the big one, using mode W by accident erases existing content instantly. So always double check before you use it, and prefer append when you actually mean to add rather than replace. Let's gather the habits that'll keep your file code clean and safe. Always open files using with. Handle errors with try and except so a missing file doesn't crash you. Use append mode when you're adding data rather than overwriting. Keep your file paths organized so Python can find things. And avoid reading very large files all at once with read. Loop through them instead. Follow these 5 and you'll steer clear of most file headaches. Now it's your turn to practice. Try creating message.txt and writing hello Python into it. Then read that same file back and print its content. Append 3 names to names.txt. Count how many lines are in a file, and ask a user for their email, and save it to emails.txt. The tip here is a good one. Combine open with try, and except so your solutions stay robust even when a file is missing. Let's take a breath and recap. Lesson 3. You've learned how to open files with the open function, how to read their contents, and how to write and append data. You've also seen how the with statement makes file handling cleaner and safer, and how to handle file errors gracefully, plus why persistent storage matters in the first place. Next up, we'll take all of this and build a real project, a simple login system. Here's our first project, and it's a fun one, a simple login system, part of Module 3. We're going to build a register and login program that stores real accounts in a text file, so this is file handling in action. Users will be able to register, log in, and have their details verified against what's saved. In short, we'll read, write, and verify real user data, tying together everything the lesson just covered. Let's set the objective clearly. We're building a simple login system in Python that uses text files. Users register with a username and password, and then log in later with those same saved details. Along the way, you'll practice creating and using text files, writing and reading data, appending without deleting old accounts, working with functions, loops, and conditionals, and handling errors with try and except. The main goal, as the note says, is practicing reading from and writing to files. Before we write code, let's picture how the whole thing works. The program shows a menu with 3 choices: register, login, or exit. Register asks for a username and password and saves both to users.txt. Login reads that file and checks whether the credentials you typed match a saved account. And notice the file format on the right, 1 account per line, with the username and password separated by a comma, right after a header row. Let's build the register function. First, we collect a username and password and strip off any stray spaces. If either one is empty, we print a message and return early, because we don't want blank accounts. Then we try to open users.txt and loop through it, splitting each line at the comma to check whether that username already exists. If it does, we stop. If the file isn't there yet, the accept quietly passes. Finally, we append the new account and confirm success. Now the login function, which mirrors register but checks instead of saves. We ask for a username and password, again stripping whitespace, then open users.txt and loop through every saved line, splitting each one at the comma. If both the username and the password match a stored pair, we print login successful and return. If we reach the end with no match, we say the username or password was invalid. And if the file doesn't exist, we report that no users are registered yet. Tying it all together is the main function, our menu loop. We wrap everything in a while, true loop, so the program keeps running for repeated actions. Each time around, it prints the 3 options, reads the user's choice, and calls the matching function. Register for 1, login for 2, and for 3 it says goodbye and breaks out of the loop. Anything else prints invalid choice and simply loops again, so the menu never leaves the user stuck. Let's see the program actually running. In the register panel, the user picks option 1, types a username and password, and gets registration successful. Then in login, they choose option 2, enter those same details, and it welcomes them back by name. But look at the wrong login on the right. A bad password gives a clear, invalid username or password message. As the checkmark notes, the program guides the user at every step instead of crashing. The project works, but let's stretch it further with a few challenges. Try displaying all registered usernames, counting how many users are saved, letting users change their password, or allowing an account to be deleted. Now, one serious note in red, and please take it to heart: never store real passwords as plain text. Real production systems use hashing, encryption, and proper databases. This project is purely about learning how file reading and writing works. Let's move on to lesson 4, where we meet JSON. JSON is a lightweight format for storing and exchanging structured data, and it's basically the language of web APIs. As the preview on the right hints, we'll be using loads and dumps from the JSON module to move data back and forth. So think of this as the data format that powers modern apps, and by the end, you'll be comfortable reading and writing it in Python. So what is JSON exactly? The name stands for JavaScript Object Notation, and it's a lightweight format for storing and exchanging data. Here's the part that'll make you smile. It looks almost identical to a Python dictionary, as you can see in the example with name, age, and is_student. It's widely used in web APIs, configuration files, databases, and for communication between applications. Just one heads up in the note: JSON writes false, true, and null in lowercase. The great news is Python already ships with a built-in JSON module, so you don't install anything, you just import it before use, exactly like the one line shown here. Once it's imported, this module lets you do 4 key things: convert JSON into Python objects, convert Python objects back into JSON, read JSON from files, and write JSON to files. Over the next few slides, we'll walk through each of those conversions, one step at a time. Let's start with turning JSON into Python. The function JSON.loads takes a JSON string and parses it into a Python object, and a JSON object comes back as a dictionary. In this example, we start with a JSON string holding a name and an age, run it through loads, and print the result. The output shows a normal Python dict, and checking its type confirms it's a dict. A handy way to remember it: loads means load string. Now let's go the other direction, from Python to JSON. The function JSON.dumps takes a Python object and serializes it into a JSON string, so a dictionary turns into a JSON object. Here we take a person dictionary with a name and age, run dumps on it, and print both the result and its type. The output looks like our data, but notice the type is now str, a plain string. The memory hook here, dumps means dump to string. Those last two worked on strings, but usually you want to save straight to a file. That's what json.dump without the s is for. It writes a Python object directly into an open file as JSON. Here we build a dictionary with a name, age, and country. Open data.json in write mode using with, and dump the data right in. The note captures the key distinction. Dump with no s writes to a file, while dumps returns a string. And naturally there's a matching function for reading a file back. json.load, again without the s, reads JSON from an open file and hands you back a Python object. Here we open data.json in read mode, call load, and print the result, which comes back as a familiar Python dictionary with the name, age, and country we saved earlier. Same rule as before. Load with no s reads from a file, while loads parses a string. One more nice touch before we finish. Pretty printing. When JSON is all crammed onto one line, it's hard to read, so the indent option cleans it up with neat, nested formatting. Here we pass indent equals 4 to dumps, and look at the output. The object is spread across multiple lines, the skills list is nicely indented, and the whole structure is easy to scan. It's a small change that makes your JSON far more readable. Let's close with a reference that ties everything together. How JSON types map to Python types. The JSON module handles this conversion automatically in both directions. A JSON object becomes a dict, an array becomes a list, a string stays a str, and a number becomes an int or a float. Lowercase true and false turn into Python's capitalized true and false, and null becomes none. Keep this table handy, and JSON will always feel familiar. Let's ground all this JSON theory in something real. A huge number of web APIs hand you back data as JSON text, and Python turns that text into a dictionary you can index by key. Here we take a response holding weather and temperature, run json.loads to parse it, and then just ask for the weather value. Out comes sunny. That's genuinely how apps read data from web services. So let's pull lesson 4 together. You now know what JSON is and where it shows up, and how the built-in JSON module works. You've seen loads and dumps for strings, load and dump for files, pretty printing with indent, and how JSON types map over to Python types. Next up, we put all of this to work in a real project, a JSON to-do list app. Here's our second project of the module, a JSON to-do list. Think of it as a little task manager that can add, view, and delete tasks, and save everything to a JSON file. We'll build it around 3 functions you can see up there: load_tasks, add_task, and save_tasks. The big idea is persisting structured data, so your tasks stick around like a mini database. Let's start with the goal. We're building a to-do app that stores tasks permanently in a JSON file. It can add new tasks, show them all, delete them, and save everything back to disk. And notice the file starts life as just an empty pair of brackets, an empty list, meaning no tasks yet. This is exactly how real apps store their data permanently. Now the storage layer. Load_tasks tries to open tasks.json and read it, returning the list inside. But wrap it in a try, and accept, so if the file doesn't exist yet or something goes wrong, it quietly hands back an empty list instead of crashing. Save_tasks does the reverse. It opens the file for writing and dumps the whole list back with indent 4, keeping it clean and readable. Next, adding and viewing. On the left, add_task loads the current tasks, asks the user for a new one, and appends it as a little dictionary with the task text and a done flag set to false, then saves and confirms. On the right, view_tasks loads the list. If it's empty, it says no tasks found. Otherwise, it loops through and prints each one numbered, showing done or to do based on that flag. Now deleting, plus the menu that ties it together. Delete_task shows your tasks, asks for a number, and pops that item, converting to a 0-based index. If you type something that isn't valid, the accept catches it and warns you instead of crashing. On the right is the main loop. It prints the menu over and over, reads your choice, and routes to add, view, delete, or exits cleanly when you pick 4. Let's peek at what actually lands on disk after adding a couple of tasks. Here's tasks.json, and it really does look like a mini database. It's a list holding 2 dictionaries, one for studying Python and one for going to the gym, each with a task label and a done flag currently set to false. So every task is just a small dictionary, and the whole thing is a list of them. So what did this project teach you? You used json.load to read the file and json.dump to write it, and you combine lists and dictionaries together to model real data. Bigger picture, you practiced data persistence and structuring a whole program. And if you want to push further, try the challenges. Mark tasks completed, add deadlines, filter to unfinished tasks, or group them into categories. Now we shift gears to a new file format. This is lesson 5, all about CSV files. CSV lets you store tabular data, the kind of rows and columns you'd see in a spreadsheet or database. It's honestly the backbone of a ton of data analysis and exporting work. Python even has a built-in CSV module with reader and writer, so the whole thing comes down to rows, columns, and commas. Let's define it. CSV stands for comma-separated values, and it's just a plain text file that stores data in a table. Each line is a row, and within a row, each value is separated by a comma. Look at people.csv. The first line names the columns, then each following line is a person's data. You'll meet CSVs everywhere: data analysis, database exports, Excel, and data science. And Python's built-in CSV module handles all of it. Before you can touch any CSV features, you bring in the module, and it's a one-liner: import CSV. The nice part is there's nothing to install. The CSV module ships with Python's standard library, so it's already there the moment you have Python. No pip, no downloads. Just import it, and you're ready to read and write. Now let's actually read a file. CSV.reader walks through the file row by row, and each row comes back to you as a list of strings. Here we open students.csv, hand it to CSV.reader, then loop and print each row. Look at the output. Every line becomes its own list, and even the ages like 20 and 21 come back as strings in quotes, not numbers. That detail matters later. One thing you'll notice with real CSVs is that first row is usually column names, not actual data. If you don't want it, call next on the reader once before your loop starts. That single call advances past the header, so your loop begins on the real records. See the difference in the output. The name, age, grade header line is gone, and we jump straight to Ali, Sarah, and John. Since each row is just a list, you can grab individual columns by their index position. Remember, indexes start at 0, so name is row 0, and grade is row 2. In this code, we skip the header. Then for each row, pull row 0 as the name and row 2 as the grade, and print just those. The output shows each student paired with their grade, no ages in sight. Now let's write data out. CSV.writer creates and writes CSV files for you. One habit to build right away. Pass newline equals empty string when you open the file. Otherwise, you can get annoying blank lines between rows. Here we've got a list of lists, one header row and 2 people, and we loop calling write row on each. The result is a clean people.csv. Remember, write row handles a single row at a time. If looping row by row feels repetitive, there's a shortcut. Write rows, plural, takes a whole list of rows and writes them all in one call. Same setup as before. A list of lists with a header and 2 records. The file opened with new line empty string, but instead of a loop, we just hand the entire list to write rows. One line, all the rows written. Reach for this whenever you already have your data collected. Reading by index number works, but it can get confusing. CSV dict reader is friendlier. It reads each row as a dictionary keyed by the column names, so you never juggle index numbers. Here we open people.csv, wrap it in dict reader, and print row of name and row of city by their actual labels. The output gives us Ali in New York and Sarah in Chicago. Honestly, row bracket city reads a lot clearer than row bracket 2. And there's a matching tool for writing dictionaries, CSV dict writer. The one thing to remember is to call write header first so your column names land at the top. Here we've got a list of dictionaries with name and age. We open the file, define our field names, create the dict writer with those field names, write the header row, and then write rows dumps all the dictionaries out. Clean. Labeled CSV, straight from dictionaries. Let's zoom out and see why this matters. CSV files are genuinely everywhere in data-driven work. This table walks through it, exporting users from a database, loading data into Python for analysis, feeding training datasets to machine learning, moving spreadsheet data in and out of Excel, and saving system reports from logging. You'll bump into names like sales_report, employee_list, inventory, and customers all the time. Before we move on, a few habits worth locking in. Always pass newline equals empty string when writing CSV files to avoid those blank lines. Reach for dict reader whenever you care about column names. Use the with open pattern so your files close themselves automatically. And when files get large, process them with loops rather than loading everything at once. Small habits, but they save real headaches. Let's talk about 2 mistakes that trip up almost everyone. First, forgetting the newline parameter when writing. On the left, the wrong version opens the file without it. The correct one adds newline equals empty string. Second, on the right, treating values as numbers. Remember, CSV values always come back as strings, so if you need math, you must convert them yourself, like wrapping a value in int, the way convert.py shows. Time to put it into practice. Your task: create employees.csv, then write Python that reads it, prints every employee, and adds up the total salary. Here's the sample file with name, department, and salary for Ali, Sarah, and John. Break it into 3 steps. Read the CSV, print all employees, and calculate the total. And here's the hint: use DictReader, and remember to wrap the salary column in int. Here's one clean solution. We start a total_salary at 0, open employees.csv with DictReader, and loop through each row. We pull the name by its column, convert the salary to a real integer with int, print the person, and add their salary onto the running total. After the loop, we print the total. The output lists each employee and finishes with a total salary of $15,500. DictReader plus int turns text rows into real calculations. Let's wrap Lesson 5. You now understand what CSV files are, how to read them in Python, and how to write them back out. You've worked with CSV Reader and CSV Writer for list-style rows, and DictReader and DictWriter when you want column names, and you've seen where CSV shows up in the real world. Next up, we tackle something every production system needs: working with dates and time. Welcome to Lesson 6, Dates and Time. This is where things get real, because timestamps, scheduling, expirations, and time zones are absolutely critical in production systems. The main tool is Python's datetime module, and you can see the pattern up top. Import datetime, then call datetime.now to grab the current moment. Our goal here is to handle time the way real production systems do. Let's set the stage for why this matters. On the left, all the places you'll need it: timestamps and logs and APIs, token expiration and authentication, cron jobs and scheduling, billing cycles and finance, and keeping time zones consistent across distributed systems. On the right, the tools Python gives you: datetime for the core work, time for low-level operations, zone info for modern time zone support, and calendar for calendar utilities. First, the core types you'll import from datetime. There are 4 to know. Date handles just the calendar part, the year, month, and day. Time handles just the clock part, hour, minute, second. Datetime combines both, a full date plus time. And time delta is special. It represents the difference between 2 times, a duration. Keep these 4 straight, and the rest of the lesson clicks into place. Now, getting the current time, and there's a right and a wrong way. On the left, datetime.now by itself gives you the moment, but it's naive, meaning it carries no time zone. That's fine for quick scripts, but not safe for production. On the right is the production version, pass timezone.utc, so the time is anchored to UTC. The rule to carry with you is simple: always use UTC internally. You're not limited to the current moment. You can build specific dates and times by hand. On the left, we create a full datetime by passing the year, month, day, then hour, minute, second, all as arguments. On the right, when you only need part of it, you can make a date on its own with just year, month, day, and a time on its own with hour and minute. Pass only the pieces you actually need. Once you have a datetime, you'll often want it as readable text, and that's StarfTime's job. You hand it a format string full of codes, and it turns your datetime into a formatted string. This table is your cheat sheet. Capital Y for the 4-digit year, lowercase y for 2 digits, M for month, D for day, H for 24-hour, I for 12-hour, and over on the right, M for minutes, S for seconds, P for AM or PM, A for the weekday, B for the full month name. StarfTime is the mirror image. It takes a string and parses it back into a real datetime. But here's the catch you must respect. The format string you provide has to exactly match the text you're parsing, or Python throws a value error. In the good example, we parse a dash-separated date with the matching dash pattern. The mismatch box shows a /formatted date, which would fail against that same pattern. Match them precisely. Here's where time delta earns its keep. It represents a duration you can add to or subtract from a datetime. On the left, we compute a future date by adding 7 days to now, and a past one by subtracting 5 hours. On the right, you can see the arguments it accepts: days, seconds, minutes, hours, even weeks. Mix them however you like to shift a datetime forward or backward. Good news: comparing dates is refreshingly simple. Python compares datetimes chronologically using the regular comparison operators you already know. On the left, we just check if future is greater than now and print a message, no special conversion needed. And on the right, if you subtract 2 datetimes, you get back a time delta, so you can ask for its days or its total_seconds. Subtraction between datetimes always yields that duration object. Let's talk timestamps, sometimes called epoch time. A Unix timestamp is simply the number of seconds since January 1st, 1970 in UTC. It's a compact, universal way to store a moment. On the left, now.timestamp gives you that number, and from timestamp turns it back into a datetime. But heed the production rule on the right. When you convert a timestamp back, always attach UTC using zone info so you don't lose track of the zone. Finally, the piece that causes the most real-world bugs: time zones. In modern Python, reach for zone info to make your datetimes time zone aware. On the left, we build a UTC time and a New York time using zone info. On the right, a time zone converts one zone into another, Here shifting UTC into Los Angeles time. And the warning is worth repeating. Never use naive datetime. Now in production, always attach a time zone. Let's talk about a subtle trap. Naive versus aware datetimes. A naive datetime carries no time zone at all, while an aware one knows exactly where it sits. Here you can see one made with just now, and another anchored to UTC. The moment you try to compare a naive one against an aware one, Python throws a type error. My advice? Pick one style, aware, and in UTC, and use it everywhere. Now that we're staying aware and in UTC, how do we hand a date off to another system? That's where ISO format comes in. Calling it on our datetime produces this clean standard string, with the date, a t, the time, and the offset all in one. This is the format APIs everywhere expect, so whenever you're sending dates through an API, reach for ISO 8601. Next, let's drop down a level to the time module. It's lower level than datetime but incredibly handy. Calling time gives you a raw timestamp, and sleep simply pauses your program, here for 2 seconds. Over on the right, notice the timing trick. Grab the time before, grab it after, and subtract. That's how you measure how long code takes. And sleep is essential when you're scripting or rate limiting. The calendar module is another small helper worth knowing. It gives you handy utilities for months, weekdays, and leap years. On the left, we print out a whole month for April of 2026, and on the right, iSleep quickly tells us that 2024 was a leap year, returning true. So when you need to build calendars or validate dates, this module has your back. Let's see these ideas in real code. Here are 3 patterns you'll meet constantly. First, expiration logic, deciding if a token or session has aged past its window using a 1-hour time delta. Second, scheduler logic, checking whether enough time has passed since the last run. And third, logging with a UTC timestamp and ISO format. These same patterns quietly power authentication, logging, and background jobs everywhere. Here's a favorite beginner example. Calculating someone's age. On the left, we subtract birth year from this year, then nudge it down by 1 if their birthday hasn't happened yet this year. On the right is the main block. We ask for a birth date, parse it with strop time, and wrap it in a try, except so a bad format prints a friendly message instead of crashing. Let's talk about the edge cases you simply must handle. Daylight saving time is handled for you automatically when you use zone info, which is a relief. Leap years you can check with iSleep. And watch this one. Asking for February 30th raises a value error, because that date doesn't exist. The takeaway is simple. Always validate every date input before you trust it. So how do the pros handle all of this? Here are the golden rules. Always store your time in UTC, and only convert to a local time zone right at the UI level. Use ISO format for APIs, and never store pre-formatted strings in your database. Avoid naive date times, lean on time delta for calculations, and validate every input. In short, UTC everywhere, convert at the edges. Let's pull it all together in a mini project, a small event system, built the production way. Notice how every timestamp is time zone aware and stored in UTC. When we create an event, the start time is now in UTC, and the end is start plus a time delta. The is_active method just checks whether right now falls between them. Create a 60-minute maintenance event, ask if it's active, and you get a clean answer. That wraps up Lesson 6. By now you fully understand date time, and time delta, plus formatting and parsing dates and doing time arithmetic and comparisons. You've also seen timestamps and epoch time zones, which are truly production critical, and the real-world system patterns that tie it all together. Next up is a project, building an employee management system. Time to build something real. This is Project 3, the Employee Manager. It's a menu-driven program that stores employee records in a CSV file, which acts as a mini database. You can see the core actions: add, view, and search. The big idea here is treating a simple CSV file like a real database. Our goal is a Python program that uses a CSV file as our database. The program needs to add new employees, view everyone, search by ID, and exit cleanly. Along the way, you'll practice using CSV readers and writers, managing file creation and appending, and handling loops, conditionals, and user input. Step 1 is creating the CSV file itself. We create, quote, employees.csv, with a header row and a few starter records to act as our database. That header row is vital. It defines the column names, ID, name, department, and salary, which allows our program to correctly read each record below. Now let's set things up. We import CSV and OS and define our file name. The quote, create_file_ if _not_ exists function checks if the file is already there, and if not, writes the header row. For adding, we pin the file in append mode, which adds a new row at the end without erasing previous data. For viewing and searching, we use dict reader, which turns each row into a dictionary. View_employees loads the list and prints every record. Search_employee prompts for an ID and loops through the rows to find a match. Once found, it prints the details and flags it as found to exit the loop. The main menu is the program's heart. It runs in a while-true loop, repeatedly printing options and reading user choice. Depending on the input, it calls the appropriate function. It only stops when the user selects the exit option, which breaks the loop and displays a goodbye message. Let's see it in action. Choosing option 2 displays all our employee records, while option 3 lets us search for a specific ID, like Sarah's. Adding a new employee via option 1 is straightforward and confirms the success of the operation. It's rewarding to see the full program run smoothly. To make our program more robust, we can add validation. By wrapping the salary input in a loop and using the method, we ensure the user enters a valid number. If the input is not numeric, the program displays an error message and keeps asking until a valid digit is provided. There are plenty of ways to challenge yourself here, like preventing duplicate IDs or calculating total salaries. This project is a great learning tool because it demonstrates data storage, search logic, and persistence, bridging the gap toward real back-end development. Moving on to virtual environments. The goal here is isolation. By keeping each project's dependencies separate, you prevent library version conflicts and keep your global Python environment tidy. It is a best practice to have one clean, isolated environment for every project. A virtual environment creates a sandboxed space for your Python packages. It allows different projects to use conflicting library versions without issue. Without this isolation, packages install globally, which frequently leads to environment instability. Here is why this matters. If Project A needs Django 4.2 and Project B requires 3.2, a global installation will cause an overwrite. Virtual environments allow each project to maintain its independence, ensuring that they only use the specific library versions they require. You don't need to download extra software to get started. Python ships with a built-in module called venv that handles everything. Because it's built in, there's no complex installation process. The tool is already waiting for you on your machine. Creating an environment is easy. Just navigate to your project folder and run python -mvenv. This creates a folder named venv in your directory. This folder contains all the isolated tools and packages needed for your project, ensuring your development stays organized. Finally, remember to activate your environment. On Windows, run the activate script located in the scripts folder. On Mac or Linux, use source on the activate file in the bin directory. You'll know it's working when you see the venv prefix in your terminal prompt. Now that it's active, let's install something. Once activated, any package you install applies only to this project, not globally. Here, we run pip install requests, and it lands inside your project's venv folder. This keeps every project's dependencies neatly separate, so nothing you add here can leak out or affect other projects. How do you check what's actually installed? Just run piplist, and it shows every library in the currently active environment. In this output, you can see our package quad requests, listed with its specific version number. It's a quick way to confirm your environment setup is exactly as you intend. Professionals share their setup by recording dependencies in a requirements.txt file. Running pip freeze and redirecting it into that file writes out every package with its exact version. Then, another developer can use that same file to recreate your exact setup with just a single command. When you're finished working, you should close things out properly by deactivating. It's as simple as typing deactivate in your terminal. You will know it worked because the venv prefix on your command prompt will disappear, indicating you are back to your standard system environment. Let's look at a typical professional project structure. A standard project keeps its environment, source code, dependencies, and documentation organized side by side. The requirements.txt file is particularly important here, as it acts as the master list that allows anyone to easily rebuild the project environment. Let's review the best practices. Always create a unique virtual environment for every project. Never commit the venv folder to version control systems like Git. It's too large and machine specific. Instead, share your requirements.txt file. And remember, always activate your environment before you start installing any new packages. Here is a real-world workflow to start a new project. First, create and enter your folder. Second, create your virtual environment. Third, activate it. Fourth, install your necessary libraries. And fifth, generate your requirements.txt file. Follow these 5 steps to ensure your project remains isolated and perfectly reproducible. Here is a quick summary of why we use these environments. They isolate dependencies, prevent package conflicts, and help manage library versions. We covered 5 essential commands: creating, activating, installing, freezing, and finally deactivating. Keep this cheat sheet handy, and you'll manage your development environment like a pro. With that, Module 3 is complete. You have mastered essential skills, including modules, error handling, file operations, JSON and CSV data, and virtual environments. You now have a professional-grade toolkit for building robust, data-driven Python programs. You should be proud of your progress. Great work.